Just bear with me a minute. I found that I couldn't unmute myself while I was screen sharing. So okay. Is that all visible now? Oh, hang on. Can you hear me?
We can hear you, but we can't see your screen. Just we can see you. You're not sharing?
Oh, I thought I was. You know, what the hell's going on here? Let me. I thought. Are you seeing? Oh, what the hell's going on here? Are you seeing our PowerPoint thing on the screen?
No.
Yeah. Because this says I'm sharing a screen. Oh, I need to click share.
Do it every time.
That's better.
Yeah, okay. That's not the one I want. I'm feeling stupid at the moment. Is that sharing?
Yep, looks good.
Okay. This is just a summary of, well, it's a fair bit of statistics about what's going on in the worldwide stuff, plus a few of the what's happened internationally. But let me go through the statistics because I think there's some interesting things to learn out of it. The number of observations continue to grow, as you can see from that plot. Been a huge growth over the last 5 years. I get the sense that the growth is flattening off, but time will tell. It's only partway through the year, and in the reporting process, the Americans are well behind in their reporting. They've got some issues there. So we're on one aspect of it, we're a bit behind in knowing what's happening with the total numbers. But you can see how, as Gaia has become involved, a number of successful observations have gone up. And I probably should emphasize in here that from 2020, 2021, 2022 is when Horizons imported the Gaia DR2 asteroid astrometry into its database, and that had a significant impact on the reliability of our predictions. This is an interesting plot of how many of our reported observations are dubious or worse. Let me put it that way. Back in the days of visual observations, 1994, 70% were unreliable. Visual observing periods, huge problems with reliability. As we adopted video during the 2000s, you can see how it's dropped, and from 2008 onwards, it's been a fairly consistently around 2 or 3% of observations are dubious, so that we don't report astrometry on them. This is just looking at the worldwide group of observers. Worldwide in 2022, there are 405 observers. And you can see the total number of observations there. And when you think about the number of people we have in TTOA, the number of observations we are getting is well above our weight. We're doing very well number-wise. Now, one of the interesting things looking at these figures is I've listed 2022 and 2020 and giving the numbers by asteroid diameter. If you go back to 2020, Europe was getting a lot of events with less than 10-kilometer asteroids, and no one else was getting them. 2020, everyone's getting them. I think what happened after 2020, I think people suddenly realized, hey, these small things are worthwhile doing. And I have to say myself, go back a couple of years, a 5-kilometer asteroid, I wouldn't worry about trying to find it. These days, 5 kilometers, I've got a reasonable chance with that. Not that I get many 5 kilometers, but 7 or 8 kilometers is not unusual. And that's come about because of the Gaia asteroid astrometry being included in the Horizons database. Now, this is perhaps a little bit of a sobering plot to indicate what's actually happening with our observations. This is a plot of the growth of observations, or the number of observations by year, based on the number of positive chords. Right down the bottom is where you got major events where you got 10 or more chords. And they continue to be very small. Such observations require a fairly dedicated effort with the ability to get a large number of people, typically in a relatively co-located. Typically, you'd have a group of people in one part of the country and maybe another group of people in another part of the country, but a major coordinated effort, mainly done in the US. We get some decent results out of Europe, but there's no travel involved with that. 4 to 9 chords, a bit easier to organise, but the growth of that is not being particularly great. But when you get to the smaller chords, 2 to 3 chords or 1 chord events, the growth has been phenomenal. The 1 chord event has the advantage of people such as myself and Bill and Dave Galt and Peter Nosworthy. You just stay at home and monitor everything that comes over. And the reliability of the predictions is pretty good. And you get a huge increase in single chords. And then when you have people close together, such as Dave Galt and Peter Nosworthy, or myself with John Newman and Bill Hanna, then there's potential for multiple chords. So that's had a significant growth as well. Now, the interesting thing with this is that when you come to the precision of astrometry, the results you get with small asteroids, which is where we're getting the major growth, the smaller the asteroid, the greater the precision of the astrometry, because it becomes a function of the asteroid's diameter in milliarc seconds. So if you've got an asteroid where its diameter is 2 or 3 milliarc seconds, then the astrometry result will be down around 1 milliarc second, whereas if you have a 10 or 20 milliarc second asteroid with a couple of observers, the actual astrometry accuracy works out a bit worse. So it's an interesting thing that the smaller the asteroid, if you have success, the smaller the asteroid, the better the astrometry. And in fact, the small asteroids, smaller than about 8 kilometers, our astrometry is better than what Gaia can produce as direct astrometry of an asteroid. This is another interesting plot is number of observers per event, an overall average. It's pretty much reduced from 2000, where it was about 7, frequency of well-organized campaigns, but not a large number of them. Whereas in recent years, not many highly organized campaigns, people staying at home and observing what comes their way. And we seem to be averaging out now at about 2 observers per event. That's 2 observers, including miss-observers, with 2 observers per event. The other interesting thing is to look at the number of observers that are involved. And we can see that compared to 2000, the number of regular observers we have has doubled. And it's been more or less constant for the last 5 years, up around 400 odd observers. Some variation, but it's perhaps it'd be nice to have that number increase, but it's good to have some stability there. On the increase side, we've got the EV scope from Unistellar, where we have observers getting results around the world, and that potentially can increase the number of observers, but there's some ongoing issues there we're still working through. Now, double stars. Steve's mentioned this a couple of times there. The interesting thing is the separation used in the range of 1 to 100 milliarc seconds. The things we discover are almost, I'm not aware of us finding a double star in an occultation which was previously known. They're all new discoveries, and the resolution is far better than the typical, well, any traditional double star measurement doesn't have the resolutions we have, and even I forget the word for it now, the speckle interferometry. Even speckle interferometry can't get down to the type of resolution we get, which can be better than a milliarc second if you've got multiple observers. Here's a list of 15 doubles discovered in 2022. And you can see there's column for separations, the range of values there. A valuable source of data. The big problem is we're pretty crap at doing anything with the results. Since Brian Loader had to retire from his activities in this area, things have fallen a bit into the heap about how we get papers put into the Journal of Double Star Observations. And when I have some spare time, which should come up soon, I want to have some discussions with the editors of the Journal of Double Star Observations to see if we can put forward a standard template which observers can use to create a basic paper which meets the JDSO observation needs and makes it easy for our observers to do a paper without having to do anything other than put in their observations, such as a copy of their light curve and a copy of the graphic solution and just a couple of words about, my name is Fred and my telescope was here type of thing. Just to make it easier for this type of work to be disseminated to the observers who really have, I'd like to think they could see the value in having their discoveries properly documented in the professional environment. Anyway, going through a number of events, mainly Europe and Japan, I think these ones are selected from. The top one is an interesting one where the very well-defined chords, all self-consistent, and the shape model is clearly not correct for it. There's a light curve that has got into the system, which automatically pops up in the observations editor, and you can see that's a really clean light curve. And there's some info about the diameter observations. Down the bottom, I've got a plot of an event of the same asteroid observed. I won't say which country or region it was observed in, but there were 3 chords, well, fairly close together, plus at the top there were 2 chords reported. This was put forward as an explanation of the profile of an asteroid to fit the chords, which is an interesting proposition. My view is dynamically that's a totally impossible shape to have any physical stability. And when you see events like that, the issue arises, well, what is the quality of the light curve? And on some of these things, you find observers trying to interpret light chords where the star is barely visible above the noise on the video, or heavily embedded in noise, all sorts of issues with the video. And if you apply different measurement techniques, things can change. And it's one of the things which I'll talk about a bit later that Dave Galt and I sort of have to deal with, is when you have an observation like this, which gets passed on through to myself and Dave Galt as sort of, hey, here is an exciting result. And people get really excited about these things. What a fantastic discovery. Then it's a matter of sitting down and asking some questions, which sometimes people don't like being asked. I actually had many, many years ago in the days of visual observation, we had a cloudy night with a group of people, and I had one person observed something and he explained it by it being the result of a hole in the middle of the asteroid, which is a fascinating concept. I'll just go through a couple more here. Our diameters, and the quite consistent here with the satellite diameters. Our residuals tend to be much better than the various satellites. And here's another one that's I'm not quite sure what I can really say to enhance these. In this one, the chords will fit both those two shape models. There isn't much to distinguish between them. Here's an interesting one where you, an interesting aspect here is up the top, you've got two short chords reported, and you can see that's consistent with a Gray's type event there. And the ones down here are all fairly good. Then you have this bottom chord. And there's no way there can be an asteroid shape, shaped in that way. There's got to be a time-based error of some sort with that chord. And that's the type of thing, again, which Dave Galt and I get tied up with sorting out. Another one here which illustrates issues with the reliability of measurements. Here we have a whole heap of chords which are very consistent with adjacent chords and fit in the lips very nicely. And we have two chords who on the reappearance side would seem to be late. And to try to hypothesize a mountain going up there and some sort of mountain going there, you're really looking at extremely improbable, and the most likely cause is a problem with the recording and whether they've got too much noise. So and here's one asteroid observed 13 days apart, less than 2 weeks. Down the bottom here, an occultation curve for one of the chords on this bottom one, very clearly well-defined curve. We get 74 kilometers from one and 75 kilometers from the other. The satellite diameter is all very consistent. I do an analysis for all our occultation events where you get 75 plus or minus 3, and our uncertainties there is better than all the various satellites.
Can I butt in, Dave?
Yeah, what's that, Dave?
I just wanted to mention about the little light curve diagrams that you got on showing here. At the moment, these light curves are a volunteer basis, kind of, sort of. But I just thought I'd mention that if somebody gives includes a Tangra light curve file or a CNV file in with their observations, when I put it through IOTA to check the analysis, it's only a few clicks for me to create a light curve for the observer, so that the basis of their observation are forever recorded at Vizier. So if you prefer to do your own, let me know, and that'll save me from doing it, but I'll do it anyway. So
Thanks, Dave.
I don't.
And I should perhaps somewhere along the way show some of the not so good light curves that people are submitting and say I've got a definite event. Anyway, Calliope, nice fit there. And there's a paper came out in Astronomy and Astrophysics today where I suspect there's going to be a new shape model for Calliope and its satellite Linus, where they've used mutual occultations of the system together with our occultations to get a better shape model. And it's interesting, our diameter for Calliope is significantly smaller than Iris and Neowise, but they've got huge uncertainties in there as well. And here we're getting 166, 164 Neowise, and Acua much larger. It's a nice one of Hermentaria, Japan. I'm not sure what else I could say about those. And it's nice to see the chords all fitting nicely here. But hey, with this one here, it's interesting to look at the alignment of the chords. And when you see a chord displaced at similar amounts in the same direction at both ends, you start wondering about whether there was a time-based error. And you've got to wonder about both this red line and this green line. Are they both affected in some way by a time-based error? And who knows? And maybe even that one. In these time-based errors or whatever are smaller than their quoted uncertainties. So there are issues floating around about the reliability of event times, which come through. Phaethon, small diameter asteroid, 5 kilometre diameter, and very good resolution there. And that's it. I'll stop the share. And I'll take any questions.
Dave, you mentioned about possibility of time-based errors. Do you have any indication whether they were using video time inserter or other timing methods?
It's not limited to a single time source, if I could put it that way. Most of them, the situation, most people claim their time base is GPS based. But then becomes linking issues with the CMOS cameras these days, how that happens. Whether there's issues in the data reduction about camera correction being applied properly, and that's a potential trap. The EV scope used to have major problems there with their using the mobile phone, but that seems to have been resolved, certainly at the time resolution there. But beyond that, there's no obvious cause that I can see. There's no aha moment. Somebody's definitely doing something wrong. But there's, from my point of view, an issue like floating around, which, while we have the various measurement tools doing great results and producing highly accurate times, there's a question of, well, if that's the case, why are we getting these discrepancies? And
it just strikes me, having well, been new to occultations. I've only been doing my own for roughly a year. Started with the Kiwi video time inserter and then moved to doing GPS timing. Also done tests and stuff on the EV scope. My experience was that there was pretty good guidance on how to use the video time inserter, reasonable guidance on how to use the software so you don't mess up the times during the light curve or iota processing, but it's still possible to do it there. My experience of shifting to GPS timing and attempting to use NTP as the guidance that's available for that is hard to find, and there's no consistent sort of workflow or guidance in there. I ended up sort of developing my own methods for doing the timing. I've been very careful in doing it. It's about time I did some more calibration checks myself against the analog video, but it just strikes me that that's a weakness that the timing community has. There's a lack of good documentation and protocols, and a lack of a good way of verifying that your timing is correct. There's, trying to calibrate this stuff yourself is actually quite a tricky proposition. You can do it, but it does take care. So given that, the main thing that we're trying to do is get good timing, there is, I think, an urgent need to update the documentation and the guides to cover particularly timing with CMOS digital cameras, but also the various timing methods that can be used.
I agree with all of that. Some of this should NTP, unless you got a home set up like you have, as I understand it, NTP can be significantly unreliable. And there's 2 or 3 observers in northern Italy who use NTP over a phone line, I think, and their times are always out by half a second or more. And there's been efforts made for them to use a different bit of software or whatever to do it, and they're not interested in doing it. They think their observations are useful at some level and put them in. So you've got a raft of challenges with a diverse group of observers we have, and unfortunately you can't force them to do anything.
You can't force them to do anything, but if there are well documented procedures that are what's the word for it? Certification is the wrong word, but recognized by the likes of IOTA as, this is our recommended practice, this is how you should be doing it, here's a protocol that you can follow, then that will encourage people to adopt them, because basically it's usually easier to follow a well-established protocol that somebody else has designed rather than make stuff up for yourself. My experience of NTP time, and I only use it to make sure I've got the UTC second. It would have been nice to use it as a primary time source, but I just use it to get the UTC second, so I don't have to log my GPS flash times. I'm just using it to get to the nearest second. Usually it's pretty good. Usually when I check my offset, I'm sort of around 10 milliseconds or less. For some unknown reason, yesterday it was 150 milliseconds. A GPS flash time, and I did measure the entire timing delay. So I just put in a report yesterday when my total acquisition delay was 161 milliseconds, when it's usually 3 milliseconds or 10 or something like that. So yeah, it can vary, and that's my home setup. That's my usual setup, exactly how I normally run it. Laptop had been running for a reasonable amount of time, and just for whatever reason, it was just that far out. So I don't know why. I don't particularly need to know why, because I'm measuring the entire offset each time. Yeah, but yeah, I would like to see that, and whatever update is done to the processes, that there's some very solid protocols put in place to be able to use GPS flash timing. There's very little that's documented on it. It's quite hard to find, and yeah, it's just not well supported in the community at the moment.
Yeah.
Okay, one thing I remember a couple of years back, someone produced a paper, I think in Journal of Occultation Astronomy, about using lunar occultations to check the accuracy of your system on a statistical basis, because those predictions now are apparently very accurate and reliable.
Yeah, I think that was Dave Galt. I thought that was one of yours. You and Histo did that.
Yeah,
I tried following that methodology when I was getting the GPS timing and investigating NTP timing. And yeah, my opinion on that is that you can do better. So basically that was to establish the overall accuracy of your NTP timing and camera delay, so that you could have, I suppose, a reasonably conservative statement that this is my generic or typical accuracy, to avoid having to, so you can use NTP as your primary time source and have a realistic and conservative estimate of the timing error. My experience is it's just easier just to GPS flash your recordings, calculate your total acquisition delay every time. You know, there was, to me, it just seemed a unnecessary solution when GPS flash timing can be done so easily.
The flash timing of CMOS cameras is very popular in Japan, and they mostly use iMovie for analysis of their recordings, and they have a version of iMovie that takes records the flash and then records the event and processes the event times accordingly. But there's, I think Pi-Oat slash iMovie can do that, I think. But I don't know.
Yeah, it's in for Pi-Movie. You have to have, ideally you have a long flash. So it needs to be a flash that extends over a number of frames, so that the event kind of looks like an inverse occultation, that it goes bright and then goes dim again. To do that, you need to use like Astro Flash Timer, or you actually need to have a flash unit where you can alter the time. Which basically means that you can't use an off-the-shelf little GPS USB dongle like they use in Japan, because you'd have to modify circuitry. So I looked into doing that.
Yeah.
And I decided not to build myself any more electronics.
Yeah, fair enough.
So basically, there's a number of different ways of doing it, and you know, if you follow the way, exactly the way that Join does it, and you can get the software to work, that's fine. If you want to use the priority one, then you need to build Bob Anderson's version of a flash timer that has an extended pulse, or get a chrono flash or something where you can do it. So there's no. My experience was that it wasn't really. There wasn't really sort of an off-the-shelf solution that you could get that was easy. Most of it required using, you know, particular versions of software, processes that, you know, weren't easy to do, or actually having to build electronics to do it. I've come up with a way. Then I'm just using the GPS flash dongle on its own. No electronics build required. So I have a method that I think does work well. So I'll be definitely supporting that to go into the mix of the possible methods. It's unnecessarily difficult to get started with it. And there's, you know, a lot of people cannot build their own electronics. I've got some basic skill in there, so potentially I could. If you happen to custom make devices, if you happen to do your own software analysis or whatever, then that's a significant barrier for people to do it, and also gives the opportunity for, you know, mistakes to be made when people don't actually do it properly.
Michael, can I ask, have you looked at using the Mia time to synchronize the PC clock?
Yeah, I have. I tried doing that. What's happened now with the move away from a hardware serial or parallel port with a hardware interrupt, it's now all done via USB, and USB has delays.
Yep.
So using the VK127 GPS dongle, which is the one that Join uses in Japan, it's available off Amazon for like $12 US. That you can plug into a USB port, and you can set up BK time sync or any of the NTP timing programs. I'm using Mindberg NTP, and you can read the MEAI sentences. Trouble is, they come in with an 80 to 120 millisecond delay on my PC, and it's probably going to be different on each PC. So you can use it, and this is what they use in Japan. You can use it to reliably get the nearest UTC second, but there will be a delay. That offset is reasonably consistent. It's not completely consistent. I did some sort of tests. It was maybe on my system stable to like 10, 20 milliseconds or something like that. But basically, it ended up being a hell of a lot of work. Whichever these methods, trying to use NTP as a primary source, trying to calculate whole system delays using linear occultations, a hell of a lot of work to get to maybe 10 millisecond to 20 millisecond accuracy.
Yeah.
When if you just GPS flash.
Yeah, the flash, you still need the flash. Yeah. I'm just thinking as a way of knowing you've got the right second. That's all.
Yeah, so it is viable for doing that. I've actually came across there's a program called BK Time Sync or something, which is used in ham radio, where you can just use that to do a brute force horrible clock time synchronization rather than the
I tried it recently. It didn't work all that well for me, but Nemea time too worked quite well.
Yep.
I was planning on writing it up. I was going to do an investigation, try and figure out what the latencies are. I just thought I'm not going to reinvent the wheel if somebody else has already done it. Yeah,
I haven't tried using MEA time. I've been using Mindberg.
Right, okay.
There's a guy carrying.
It popped up in the IOTA mailing list in the last 24 hours or so. Someone was saying they were using it, that combination of the VK172 plus a Nemea time.
Yeah, I'm still. I have had some correspondence with that person, Karim Saki.
Gotcha. Okay. Yep.
Yeah, I personally don't believe that he's getting millisecond time and accuracy with the system.
That is what Nemea time 2 claims, and I don't believe it either.
You can synchronize your PC to that precision. My experience on my laptop, it's an old laptop, it's about 8 years old, is there's time drift based on processing load and the temperature of the CPU. You've got to remember that all these systems are designed for, all these time synchronization systems are really designed for servers. And if you're developing a time server, you're going to have a consistent load. It's going to be a controlled environment. You're going to have much better temperature stability and load than you'll have on a typical PC. And I've seen, basically as soon as I start recording, processing load goes way up, PC temperature increases, latency on the bus increases, and my PPM, my parts per million time accuracy on the PC clock moves, and my time drifts. And that can end up being several milliseconds across the duration of a recording and sometimes more. So I've just, maybe if I use my other laptop, which is gruntier and better, I'll get less drift. But basically my attitude is that, the time is approximate, it is going to drift. So I timestamp before and after and then
clean it up
and interpolate through. But to, all the stuff has to be tested.
Right. Okay. Thank you very much.
And I'm about to try and get a better understanding, hopefully, of the actual accuracy of my timestamps. I think I'm getting about plus or minus 5 to 10% of the exposure time as my accuracy using the GPS flash timing. But I need to do some more tests to see if that's actually true. And it's a bit like what Dave said about this doing timing on small asteroids. When you do get an occultation of a small asteroid, it gives you better precision. You actually get better time and accuracy with GPS flash timing when you've got shorter exposures.
Definitely sounds like a TDSO 18 topic.
It does, doesn't it? That's right. Yeah.
It's overdue. There's at some point the old style analog video cameras will just not be viable for the majority of people, and we need to have a well-established alternative.
Yep. Very good. Any other questions on Dave's talk or the other talk we just had? Okay, Murray, you want to wind up the recording?